aberration is something called a binary status, which is a 16-bit integer. So this kind of becomes a private, a vendor-specific data space that maps this 16-bit integer into a 16-bit integer. Actually, this says bit string, but it's really an integer in the output data set. What this does allow going forward is the ability to do remote configuration using the substation configuration language tool that Ralph talked about earlier also. So a PMU can now export an IED capability description file. This file can now be used to configure any upstream device that will be receiving this data set. So security. As I mentioned, 90-5 defines end-to-end security. And it defines three aspects of security. The first one is something known as a secure hash algorithm, usually abbreviated SHA, and this level 2 at this case here. This is known as an authentication code. The way to most easily understand this is in the concept of a cyclical redundancy code. A CRC takes every piece of data in a message and runs it through an algorithm that mixes all the bits up and comes out with one number known as a CRC. The difference in this calculation is that there's the introduction of a key. So there is now a keyed approach. So how the bits are mixed up are defined by a 256-bit key. So you have a very, very unique mechanism for how to mix the bits up. The probability of somebody guessing that key and somebody duplicating that authentication is small. I think approaching 0 is in the limit it approaches 0. Let's put it that way. So this is, so if I as a publisher have a key, and then as a subscriber, that subscriber has the same key. If the subscriber, the process works like this. A message that goes through what is called the message authentication code calculation with the key and creates a message authentication code. The code along with the message is sent to the receiver. The receiver takes the message and runs it through its local calculation with the same key. If the received code matches the recalculated code, this message is authenticated. The probability of someone randomly sending that message is about 0. In fact, I think the answer is 1 divided by 2 to the 256. That's the probability of someone duplicating that message authentication code. The second part of security is the ability to encrypt the complete message. The encryption algorithm chosen for this is AES, the Advanced Encryption Standard. So there is no issue going forward. It's very, very clearly defined. The beauty of both of these today is most new, in fact, all new microprocessors contain hardware such that the calculation of the hash code and the calculation of the encryption is now done all in hardware. So we're looking at microseconds to calculate a hash for a 128-bit data frame. The last part of this has to do with how I exchanged keys. So we need the implementation from multicast must be a symmetric key. What that means is that the publisher, when it locks the message, as a subscriber, I have to have the exact same key to unlock that message. So the publisher and the subscriber have to share the same key for a given set of messages. The mechanism to do this is known as the group domain of interpretation, usually abbreviated as GDOI, and it is an internet standard known as RFC 3547. So this defines the mechanism for sharing the keys between all the devices. Now I'm going to mention on this one, on the implementation of this, Cisco with a C has said that they will provide the code to implement GDOI as public domain software going forward. And Cisco with an S has also said that they are providing information. It's posted. So the implementation of the 90-5 software that shows how to pack the data into the data set is now also available from Cisco with an S as public domain software also. The encryption algorithms, there are several choices, and this is when you as a user, you can set whether or not you want no encryption, authentication only, or authentication and encryption. And this is a setting that you as a user get to choose. And encryption, I won't go through the details, but suffice to be, I think everyone here understands the basic concepts is that I take some plain text data, pass it through an encryption algorithm with a key, the data gets sent out in ciphertext, and on the receiver side, I use that same key to decrypt the message and come back out with plain text. You have information. I am not going to explain how AES works. It's an interesting read. I read it once, and that was enough for me. 5 minutes. I'm actually just about done right now, I think. The last thing I'll mention is just a quick overview of this GDOI. GDOI can work with a authorization, authentication, and accounting system, and so that the way this will work is for a device to receive a key, it must be authenticated in the system and have a certificate. If your certificate is revoked, you will no longer receive updates of the keying, so you will no longer be able to, if the message is authentic, you will no longer be able to authenticate a message, and you will no longer be able to decrypt a message because you will no longer know what your key is going forward. And the concept of the key is that there'll be the technical report defines the concept of a key center, of a KDC, key dispatch center, is that Ralph? KDC? Whatever, KDC is, it's a HERB acronym. Key dispatch center. So the key dispatch center will send the keys out to the publishers and to the subscribers for a given set of information. And every different block of a group of transmitters will have a different key which they use. So this is an overview of 90-5, and I guess we've got time for a question or two.
Have you got any clarification questions? One or two? Okay, we have two and yeah.
Yes, Mark Day Bach from Washington University. It's not clear to me if you have shared keys.
Sure.
Two of them? Stereo. If you have publisher and subscribers share a symmetric key, what is to stop a subscriber from spoofing a publisher?
Well, the key is only distributed to devices that have certificates. So if you don't have the right certificate, you're not going to get, I'm not going to accept a key from you if you don't have, I mean, the whole GDOI process is one of authenticating who gets the keys.
But a subscriber that was compromised would have the certificate, right? Basically.
So I guess is security, one of the things I've learned is security is a moving target.
Yep.
And so we constantly have to upgrade. If someone finds a way to go and crack the 256-bit key that is used to share between these devices, which can happen, I guess, then we will have to find new ways to better secure the mechanism.
Thank you.
Yeah, this is actually a real clarification question. Back in the beginning of your discussion, you talked about how you could actually include 4, did you say, time slots of data?
Yes.
As a way to get around the fact that you could lose data in the process.
Correct.
So this would mean, is this in every transmission? So we're literally quadrupling the size of the...
So the answer is yes. For a couple clarifications. Number one, it's an option. So it's a setting in the device, and the device can say, yes, I want to send 1 or 2 or 3 or 4. It's a setting, your choice.
Okay.
Number two, yes, it is going to add bandwidth. It's not quite a doubling, and the reason is the header is a significant portion of the message. So there's one header, and then only the data set, which is pure binary, is repeated.
Okay, thanks.
Okay, I think we have one more question here. And please introduce yourself.
So is the R-Goose, oh, sorry, this is Sushruta Ravish from National Instruments. My question was, I have a couple of questions. One is the R-Goose and the R-SMV, or the new improved Goose and SMV, mainly meant for the 90-5, or is it going to be the new standard of Goose? And if so, what about the timing constraint for Goose and SMV by introducing the UDP? Would it not be lost? And the third question is, doesn't MMS do the same thing in this case?
All right. So first, 90-5 is a technical report. And as a technical report, what it defines are the changes that need to be made to 61850 to implement R-Goose and to implement R-SV. So Goose, going forward, will have an additional profile. And the additional profile will be the addition of the IP and IDP/UDP header. Will it affect timing? Yes, there's a slight delay that's added on by adding in the IP header, because now going through a network, the message has to be routed. So it will probably not have to, well, right now, what the standard says is there are timing classes, and going through a router, you will wind up in a different timing class. Then maybe you will no longer be a T5, you may be a T4 timing class going forward. So you will have to specify, but that's a function of the routed network. And lastly, going forward, there is a plan right now, in fact, maybe the chairman can comment, there is a plan to, instead of waiting for an edition 3 to include all this information, I suspect this is going to go to an edition 2 revision. To be decided. But that's one of the that's a possibility.
Okay, thank you.
Hang around for you, then I'm going to take off.
Just the two things.
Okay. Good afternoon. My name is Farnush Ramati, and I'm co-presenting with that gentleman who just finished, Mark. And we use this portion, which is about IEEE 1588, used for time synchronization. Hopefully, we can catch up with the 4 minutes that we're behind on the presentation, so we can resync our presentations. There are more slides that we can cover in the next 6 minutes, so I'll be brief. A lot of you are familiar with, well, I will try to be brief. Let's be specific. We also have data in this presentation from PG&E's proof of concept facility. That's why you see the logos at the bottom there, acknowledging that gratefully. A lot of you are familiar with IEEE 1588, used for precision time protocol. I'll just put a couple of reminders very briefly in case for those who may not be familiar. This is a protocol for microsecond or sub-microsecond time synchronization using the internet, really Ethernet, and provides a messaging system also to communicate the quality of the clock or timing and using the data frames there. In its simplest form, and you have one step or two step, newer technology, newer chips. This is a hardware-based implementation, and the newer chips have the ability to do this in hardware. Basically, between two clocks, one being a master, one being slave, one being the reference, the other one trying to sync to it, you communicate between these two, try to measure the difference in this communication time, and use that information to sync the two clocks. Basically, sync the slave clock to the master. Let's say at the time T1, let me see if this laser works. You send a message from the master clock to slave, goes through certain routes and things, it gets there. It's time tagged as T2. The two clocks may have different reference times. There could be a time difference, time offset between them, and there is a travel time or time difference there. In the old technology, you couldn't really measure T1 here to put it in this packet. You could only do that after it's sent. In the newer technology, it can be actually packed in there and sent there, so you don't need to send this again. So you would have knowledge of T1 when it was sent, knowledge of T2 when it was received. This would send the data back at time T3 that it knows what it is. Master would receive it and acknowledge that, and this would now have the information about time 3 and time T4. Having T1, T2, 3, T4, those times you could figure out what the transmission times are going this way, going that way, the references between the two, and any offset between those two. So it really gets to be as simple as that. Okay, we are halfway through the presentation if that's the case. Time tagging is at the hardware level. It is at the beginning of the Ethernet packet, a very detailed specification, and you can do time sync calculation going through that process that I just mentioned and calculate the transmission time differences. And in the newer versions, if the transmission time from master to slave or anything in between is not exactly the same, we can still calculate that. I'll skip those details. Let's get to actual some testing data. There's also methods to look at time latency fluctuations. Things are not exactly constant in a network environment. This is a little diagram showing the proof of concept testing facility at PG&E with a number of PMUs on two different switches. These switches are capable of 1588 timing distribution with a GPS-based clock providing 1588 timing. With more details, I won't get into that again. And also IRIG-B timing provided to PMUs, as well as substation PDCs, which also route data up to super PDCs. Also, please keep this in mind for the next presentation coming in a few minutes. We'll look at interoperability, which means work between any of these PMUs and the substation PDCs, between substation PDCs and super PDCs, through all network elements between super PDCs and applications or various other elements of the system. And again, operation of this clock or various types of clocks with each other. This diagram shows in more detail a testing for timing function. Basically, there is a GPS antenna with splitter going to various clocks. Some of them provide IRIG-B type signal. Some of them provide 1588 precision time protocol coming to switches that are supposed to become a grandmaster or become a transparent, in some cases configured to be slave. And sometimes the final slave is, of course, the PMU with its clock inside getting this timing signal from 1588. Again, you'll have these slides, but what I want to sort of emphasize is that this is a test setup to compare IRIG-B versus 1588 timing distribution, and we look at the scope, looking at timing signal pulses coming from various switches and clocks that have that ability, as well as the sort of more standard clocks, all different type, military grade, high accuracy, or various type. Okay, I have about 2 more minutes, or 1. Noise impairment device to look at injecting delays and seeing, okay, does this 1588 can handle the delays in the transmission of the packets, how long it can, and looking at various cases. These are some samples looking at 4 different clocks before calibration and after calibration. Here, for example, yellow is the reference before calibration, blue is our reference that's used for calibration. The pink or purplish or fuchsia, whatever you may see it as, it would be the grandmaster clock that communicates with 1588 to a slave clock, which is the green one. And you see some differences. There are different time scales on these charts when you look at the scopes. Here, look at about a quarter microsecond delay between these. Once you calibrate, they become all within specification, but you see that this particular grandmaster has a certain amount of delay, about half a microsecond or so, and its slave has another bit of delay, about 0.2 microsecond, which for this application is good enough maybe, but it would be ideal if they were a bit closer. We look at what happens if you remove GPS antenna, how fast they drift, and this is, after 15 minutes, 10 microseconds, and if you include 10 microsecond injection between the master and slave in Ethernet communication, you see that sort of 10 microsecond. In this case, that's not compensated for, properly not implemented. For example, you'll see that delay in the slave clock. I'll leave this on for you to look at. This is a summary of some of the findings, and of course devices improve, but overall lots of GPS clocks are available with better than 1 microsecond accuracy, which is of interest to synchrophaser projects. You can see good comparable data between 1588 and IRIG-B. Actually, there are some PMUs available that receive both and can compare and even report how well they are in sync, or you could use one as redundancy for the other one. For example, if you use GPS over local area and you're worried about spoofing and somebody messing with the GPS signal coming in, using a network clock from somewhat of a more distance and using that as a backup, as a comparison, is a good technique, for example. We see various devices with this range of drift, somewhere from 4 microsecond drift when you disconnect over an hour to 26 microsecond over 4 minutes. You want to limit yourself to much lower than this amount of drift to meet the requirements of synchrophaser standards. And with 1588, these are some of the findings. You can get very good clocks, but you got to make sure all details are properly implemented. Time quality is reported. One of the tests is to look at those. These are some of the time qualities in 1588.
I think we have time for one clarification question. Okay, if not, Fahid, please.
Minimize this one.
Okay, you go there.
Pull this one up.
Good.
I'm just going to this one.
Okay, maybe I'll start. Okay, here's another presentation, interoperability issues, test, and practical example. Vahid Medani and myself will cover most of this presentation. I will do a bit of a tag team. I'll start since I'm already wired. I guess that's literally so. Well, we'll talk about that later. Interoperability considerations. We got a lot of good details, I think, hammering the point that having standards is a real fundamental requirement to have practical interoperability. I can't emphasize that anymore. You really, really, really need to have good, comprehensive, practical standards to have interoperability. But please do not confuse that with each other. Having standards and having interoperability are not the same. Standards are a requirement for interoperability. They are not sufficient for interoperability. There are many things that standards don't necessarily address or they don't need to address. They provide options that many manufacturers may choose to implement or not. So they can be compliant to a standard, but may just, as a matter of function and product service, may not implement that particular function. To have interoperability, you need to actually verify those functions that you're interested in between various devices work together. That's not same as interchangeability, not another device being replaced with this one. Just the two that you want to work with each other, you got to make sure all the functions you are interested in work. And having standards in place, as well as implementation agreements, which quite often specify the details of standards or details of standards for a specific purpose. Like this 61850-90-5 implementation agreement. Those are required, make things a lot simpler, but you may need additional testing to verify interoperability. One of the other elements that sometimes is overlooked is overall lifecycle management. In your interoperability process, you got to also look at the evolution of standard, maintainability of the products, any changes you may want to do it. If the hardware platform is the same and you want to upgrade it, suddenly do you lose interoperability between two devices? Those all have to be considered in terms of overall life cycle management of products you use in your system. Again, that's another element that quite often a utility internal standard system deals with, but not necessarily industry standards dealing with that. We look at particularly in a 61850 certification program. Some of the benefits that a certification gives you is certain elements of that interoperability. If you verify conformance of certain device to certain standard, it resolves a number of interpretation differences you may have in reading a standard or understanding standard. After all, we're all human and we may read the same thing and not quite understand it the same way. I don't know about you guys, but between me and my wife, sometimes we look at the same thing and we look at it differently. Others may do that too. Early identification of non-conformances. Quite often when you start this process of looking at standard, even if you have been involved in writing those standards, you may interpret them differently, you may take shortcuts, and the devices, when you get to the field, may not work with each other. If you don't do a conformance type testing and certification, you would do what you may call natural testing, which means in the field, under difficult conditions, and it's going to be a lot more expensive to a user. You can look at the functionality and the protocols that you want to look at. You have multi-vendor solutions that need to have interoperability figured out in a bit more detail. You can work out the bugs and look at the various issues or various missing elements that a manufacturer may not or might not have implemented or might not have implemented yet. There are conformance tests, and then there are interoperability tests, and we'll get to a little bit of that detail. Not all conformance tests are interoperability tests, and not all interoperability tests are conformance tests. They all have their own places, but particularly with 61850, UCA, International User Group, provides a lot of good test facilities for conformance to 61850, as well as good additional programs, quality assurance programs, accreditation program, and also they develop approved test procedures to clarify, complete the interpretation of standards, if you like, or at least have one form of implementation agreements of the tests, if you like, in place. There are lots of benefits you get from using a product that is certified. It basically forces the work to be done up front before problems propagate a lot in the field and you have to go back and redo. Let me go to the next one. Okay, I'll use this one. Okay. What's important, and I want to emphasize again, certification doesn't address all the interoperability tests. Okay? The burden is on the user from an application perspective. Does this device serve my application? Does this serve function I want to use this device for? Okay, the device operates, talks according to standard, but does it do what I want it to do? That part is not guaranteed. interoperability test can help determine if it does its function in certain environment. Stress and performance tests. If you pass certain compliance tests, certain tests for conformance to standard, it tells you if you get these conditions, if somebody calls you and say, my name is so-and-so, you gotta